is associated with these quantum changes. Okay, so the equation that we're going to be using, right, this is the equation Bohr came up with, the amount of energy that exists between the quantum levels that are associated with each electron. Okay, and this is identified in joules, so it's an energy term. Okay, and it's 1 over n squared. N being that level where the electron starts out, where 1 is a ground state. So, first question, how much energy is associated with the ground state? You're right. Okay. The ground state, when n is equal to 1, the electron has minus 2.18 times 10 to the minus 18 joules of energy. Okay. How did I figure that out? Or how did you figure it out? If n is equal to 1, what's 1 squared? It's 1. 1 divided by 1 is equal to 1. So take this value, multiply it by 1, and then you get the energy associated with it. Okay? And for these terms, just to throw it out there, free electrons are considered to have 0 energy. Okay? Obviously, if it's a free electron, it's moving at a certain speed. It's got a certain amount of energy that's associated with it. But as far as our cases, within the hydrogen model, Bohr came up with the idea and said, look, the electrons that are free, they can't have much energy associated with the atom. Okay? Because remember, this is about energy that is within the quantum states. So if you think about it, a free electron, remember that diagram I showed you, the further we go this way, the smaller the energy gap. If n is equal to infinity, okay, if that number is infinity, you have infinity squared, which makes it an even bigger number, right? What's infinity times infinity? Well, it's super infinity. So if I have super infinity here, if you have a large number, okay, down here on the bottom of any fraction, what's going to happen to that term? It's going to approach what value? 0, that's right. So if this approaches 0 because n is equal to infinity, this entire term becomes 0. So that's why free electrons, they're going to have that 0 term associated with them. All right. So here's the question. And the question is, what is the amount of energy to go from n is equal to 2 to n is equal to 6. Remember, I wrote this in purple because I was planning on using the purple light. Let's see how much energy is associated with it. How would you solve this problem? Right, you just take the energy that's associated with level 6 and the energy associated with level 2 and find out what the energy difference is. Okay? Let's do that. Okay? Level 2, right? We have n is equal to 2. So for level 2, for n is equal to 2, we have minus 2.18 times 10 to the minus 18th joules times 1 over 2 squared, or in this case 4. So you divide this term by 4, and we're going to get an energy value that's associated with it. The energy value associated with this thing is minus 5.45 times 10 to the minus 19th joules. Okay? Now look at that value, and does that make sense? Did this value get smaller? Does this look like this is about a quarter of that value? Yes. All right, good. So it's a smaller number. All right? Now if n is equal to 6, what do we have? N is equal to 6, we're going to have minus 2.18 times 10 to the minus 18 divided by 1 over 36. Because 6 squared is 36, right? 6 times 6. Yeah? Okay, good. Okay, so let's do that one. 2.18 to the minus 18 divided by 36. So the value is, at that point is minus 6.06 times 10 to the minus 20. Much smaller term at that point. Okay? So how much energy did it take to move that electron? All right? This is important because at this point we have to look at energetics, so we have to look at the sign that's associated with it. And negative sign means energy is being released. Positive sign means energy is being absorbed. What's happening here in this case? Is the electron absorbing energy or is it releasing energy? You're right, it's absorbing energy. So we're going to be looking at a positive sign in this case. So how am I going to get somewhere with a positive sign? All right. To find out how this works, we've got to use a delta. And delta is, okay, it's something minus something else. It's a difference. The delta means difference in this case. All right? So which energy should I use first? Okay, to be absorbed. All has to do with the sign that's associated with it. If I use energy where n is equal to 6 minus energy where n is equal to 2, right? What's going to happen? Putting a minus sign in front of this term makes it large. Okay, so it changes the sign. It goes from negative to positive. It doesn't make it large, it makes it positive. Okay, so this makes it positive. Okay, so would this term be larger than this term? Yeah. Okay, so this term plus this is going to make a positive term. All right? Is that what we want? Yes, it's got to be a positive term. Okay, so let's just do the math associated with this then. So the change in energy here is going to be minus 6.06 times 10 to the minus 20 minus negative 2.18 times 10 to the minus 18. Both of these are joules. Right? Can you see both those terms? I haven't gone off the screen yet. Good. Okay, and that's going to be equal to my change in energy for this particular photon. And the math that we get, let's see. I messed up. Thank you for pointing that out. I can read your mind through that. I wrote down the wrong term. It's minus 5.45 times 10 to the minus 19. Okay? And I know you are now all red in the face because you were shouting at the computer screen going, "Oh, no, you're using the wrong term, Dr. Roy." Always double check your terms. Okay? I appreciate you yelling at your computers. All right, and what we end up with is a value of 4.84 times 10 to the minus 19. All right, and this is joules. This is the amount of energy. This is the light that we're going to be using to get there. So that's equal to E. Now, just to throw this out there, okay, how much energy is being used here? E, okay, is equal to H times frequency. Remember that C is equal to wavelength times frequency. So if I rearrange this, C over wavelength is equal to frequency. Okay, I can now take this term and replace it for that frequency term. So E is going to be equal to H times C over wavelength. If I want to know what the wavelength of the light is, and I do because I'm Niels Bohr, okay, but much more handsome, of course. Okay, rearrange the terms. So I get wavelength is equal to HC over E. Okay. So we know what the energy in the term here is. Okay. And we know what C is, and we know what Planck's constant is, right? Planck's constant is 6 point something something something, little something else, right? I've got to look it up. Physical constants, Planck's constant, 6.626 times 10 to the 34th joules per second. All right, so This term becomes 6.634, or 26. 26 times 10 to the 34th. That's joules over seconds. Okay? And I'll do this in a line diagram so you can see it a little bit better. So there's joules. C, okay, over seconds. And C is equal to 3.00 times 10 to the 8th meters for every second. That's the speed of light, right? Okay. And let's see. And what I've got left here is energy, which is joules. And joules is 4.84 times 10 to the minus 19th joules. Okay. I'm running out of space there, over on the side. I should have written it a little bit further, so let me adjust this just a little bit more. All right, push it that way. Now you can see that term over here, okay? Now when I do the math associated with it, remember that joules is a function of kilograms, okay? So I'm going to assume at this point, because I've got joules here, the kilograms in that kilograms per second squared, meters squared, all that other fun stuff is going to fall out of my equation, because I've got to use the joules conversion. And what I get out of this is just using 6.62 times 10 to the 34th times 3 to the 8th times, I put this on the wrong side. Why didn't anybody tell me? You guys should be yelling at your computers. 4.84 times 10 to the minus 19th. Okay. And the wavelength that we're going to get out, oh, I've done something wrong. Oh, that's minus. There's a minus here. There's no better way of spending your time than spending your time watching somebody do calculations on a YouTube video. And you thought you'd be watching the new Justin Bieber video. For shame. Alright, now when I get out as a value, my wavelength is 4.10 times 10 to the minus 7. Okay? Which essentially comes out to 410 nanometers. Because this boils down to meters after we do the conversion from joules over to kilograms per second. Okay? So we do that, and the joules cancel out, we're left with meters, and we get out 410 nanometers, which is just where purple light ends up. Okay? And that's how we do one of these equations. It's not entirely difficult. Okay? You just have to make sure that you watch your signs and watch how you're doing your conversions.